Hey everybody, welcome to our lecture on limiting reactants. Before we take the notes on an actual chemical reaction, I want you guys to think about some definitions that I'm going to give you, but in terms of something that you understand already, which is making s'mores. So I want you to take a look at this list of ingredients. Like, let's say we have 8 graham crackers, 5 pieces of chocolate, and 6 marshmallows. I want you to ask yourself, how many s'mores can you make with those ingredients? Hopefully you all said 4. And the reason why you can only make 4 s'mores is because you need 2 graham crackers in order to make a s'more, right? You need 2 graham crackers, you need 1 piece of chocolate, and you need 6 marshmallows. So the fact that you only have 8 graham crackers, but you need 2 graham crackers in order to make 1 s'more, the graham crackers is going to limit how many s'mores you can make. The graham crackers could make a total of 4 s'mores. And yeah, you're going to have some leftover chocolate and you're going to have some leftover marshmallows. Because if you had unlimited amounts of graham crackers and unlimited amounts of marshmallows, the chocolates would be able to make 5 s'mores. And the marshmallows would be able to make 6. Because those are only a 1-to-1 requirement in your recipe for a s'more. So the fact that your graham crackers limit how many s'mores you should be able to make makes the graham crackers the limiting reactant. And these other reactants that would allow you to make more, these are called your excess reactants. Now, the mistake that people often make is that they think that the limiting reactant is the thing you have the least amount of. And that's not true, right? Because if we look at the chocolates is what we had the least amount of, but that's not my limiting reactant. Because it depends on how many of each reactant is needed for the recipe to take place or for the reaction to take place. So it's not the thing you have the least amount of necessarily. It's also not the thing that you have the least mass of either. Because if we were massing all of these substances, the marshmallows would have the least amount of mass, right? Because they're mostly air. So even though the marshmallows have the least amount of mass, those are also not the limiting reactant. Okay, so the limiting reactant is going to depend on both the mass of the substance as well as how many moles or what number of each substance is required for that reaction to take place. Okay, so that was real easy for you to do and to understand in terms of like eyeballing some, number of ingredients for a very familiar recipe. In order to figure this out for a chemical reaction, we're going to have to do some calculations. But I'd like you to remember that the limiting reactant is the reactant that determines how much product you should be able to make. And that amount of product that you should be able to make is called your theoretical yield. It's how much you should be able to make. Now, of course, if somebody steals one of your graham crackers or you burn your s'more in the fire, maybe you don't actually make 4 s'mores, but theoretically, that's how many you should be able to make. All right, so let's go ahead and apply this to an actual chemical reaction. Okay, so of course, we always need to start off with a balanced chemical equation. So this is a reaction of copper with sulfur in order to produce copper 1 sulfide. I'm going to balance my reaction with a 2, 1, 1. Okay. Now I'm going to put my known and unknown values underneath my balanced equation. So the problem says that a chemist synthesizes 95 grams of product. Remember, the amount that you should be able to make is your theoretical yield, but that's not what this is. This right here is how much we actually made in the lab. So this 95 grams right here, I'm going to call my actual yield. And why don't you guys go ahead and define that down below in your notes. The actual yield is the amount of product actually made in the lab. Okay, now, how did we get this product? We got it by reacting 80 grams of copper with 25 grams of sulfur. Now, if we just added those two amounts together, we would find out that the product should be like 105 grams. But we're not guaranteed to react all of both of those reactants. It might very well be the case that one of the reactants gets completely used up and the other one is left over. Like we saw with the s'mores. The graham crackers got completely used up and the chocolate and the marshmallows were left over. So in order to figure out which one of these is our limiting reactant, we need to figure out which one of these reactants can make the least amount of product. Remember, that's how we figured it out over here. The graham crackers could make 4 s'mores, the chocolates could make 5, the marshmallows could make 6. Whichever reactant you run out of is your limiting reactant. It can make the least amount of product. So that's what we're going to do here. We're going to do 2 sets of dimensional analysis from copper to grams of product and from sulfur to grams of product. This amount of grams that the limiting reactant should be able to produce is called your theoretical yield. I didn't leave myself very much room for definitions here, did I? The theoretical yield is the amount of product one should be able to make once the limiting reactant is used up. So in the case of the s'mores, that was 4 s'mores. And while we're at it with the definitions, let's go ahead and define limiting reactant before we even do our calculations. The limiting reactant, again, it's not the sulfur because it's the one you have the least mass of. No. The limiting reactant is the reactant that gets used up first. It limits or determines, oh, definitely not enough room to write that word. It determines how much product should be made. In other words, your theoretical yield. Okay. So again, how do we figure that out, right? We look to see how much product each reactant can make. Okay, so we're going to do 2 sets of dimensional analysis. We're going to go from grams of copper down into grams of product. And then we're going to do a second set of dimensional analysis. We're going to go grams of sulfur. And again, ask ourselves how many grams of product can that make? Whichever reactant can make the least amount of product is your limiting reactant. All right, so let's start with the copper. We have 80 grams of copper. First things first, let's turn it into moles. 1 mole of copper has a molar mass of 63, I think, 0.6 grams. Maybe I should check my periodic table. Copper's molar mass. Yes, good. Okay, now we're going to do our mole ratio between copper and product. For every 2 moles of copper, I can make 1 mole of the copper 1 sulfide. And then I need the molar mass of the product. Let's calculate that. So 63.6 times 2 plus my 32.1 for my sulfur, 159.3. So if all of my copper gets used up, I'm going to multiply across the top here, divide by what's on the bottom. If all of my copper gets used up, I should be able to make 100 grams of product. But this doesn't take into account the sulfur at all. We have to do another set of dimensional analysis to figure out how much product the sulfur would be able to make if we had unlimited amounts of copper. So this time, let's start with our 25 grams of sulfur. 1 mole of sulfur has a molar mass of 32.1 grams. Now this was a 1-to-1 mole ratio. 1 mole of sulfur can produce 1 mole of the copper sulfide product, and then the molar mass again. All right, let's multiply that out and divide. So 25 times the 159.3 divided by the 32.1, 124 grams of product. So here's where you have to use a little bit of logic. Remember, the limiting reactant is the reactant that can produce the least amount of product. And that amount is 100 grams. And this is your theoretical yield. That's how much we should be able to make in the lab. And that means that the 80 grams of copper was my limiting reactant. This 124 grams down here is now totally irrelevant. We're never going to make 124 grams of product. Because if you think about it, we're taking copper and sulfur and putting it together and making product. Copper, sulfur, product. Copper, sulfur, product. By the time you have gotten to 100 grams of product, the 80 grams of copper is gone. It's all used up. Which means the sulfur, which could have gone on to produce 124 grams of product if there was more copper available, is now in excess. Okay, so this is what we call our excess reactant. Now, finally, there's one more thing that we can do here, which is compare how much we should be able to make, which is this 100 grams. So now we know our theoretical yield. We know the theoretical yield is 100 grams of product based on the 80 grams of copper, which was my limiting reactant. But we only made 95 grams in the lab. So why is that the case? Well, sometimes crap happens in the lab, right? Maybe one of your reactants, had oxidized or was contaminated, and so it didn't go all the way to product. Maybe, the reaction didn't go to completion because you didn't let it run long enough. Maybe you spilled some of your product. All sorts of reasons why you don't get as much as you would expect. And so we can compare those two things with something called percent yield. And percent yield is equal to the actual yield, which is what you actually got in the lab, divided by your theoretical yield, which is how much you should have gotten based on your limiting reactant calculation, times 100. So of course we want percent yields to be high. Okay, this is not percent error. This is a proportion of how much we got versus how much we should have gotten. So in this case, we actually got 95 grams. We were hoping to get 100 grams. So we got a 95% yield in this case, which is pretty good. Now, there are many other ways, well, not many other, there are a few other ways to determine the limiting reactant. However, I think this is the most efficient method. Okay, you start with the amount of each reactant that you have, and you figure out how much product each of them can make. Whichever one makes the least is your limiting reactant, and that amount is your theoretical yield. The reason why I think this is the most efficient method is most of these problems end up asking you about percent yield anyway, so it's helpful to just go ahead and calculate the theoretical yield and the limiting reactant all at once. But we will talk a little bit more next week about how we can do limiting reactant problems by comparing the amounts of reactants to each other. So you have that to look forward to. All right, see you guys in class.